Hey guys, this is a gym term 1B walkthrough. I completely forgot to make it. I apologize. I just forgot. I thought I made it the other day, but it's okay, whatever. Anyways, 1B walkthrough. This should be significantly shorter than the first one because the first one was a lot of review, which again, highly recommend if you're not sure what's going on or what you need to know. Please watch 1A all the way through. Probably put you in a better spot for the midterm exam this upcoming week. So 1B should be shorter, looking to finish within 45 minutes. Probably very likely that we will. So yeah, let's just get right into it. Also, I've seen the practice exam that was sent out, and I'm a little surprised by it. A little interested in, especially the synthesis portion. It looks like there was more reactions you're actually required to know than the ones listed on your study guide. So I have some ideas, some other, we'll do more. We'll do probably 2 or 3 more synthesis problems on this one just to cover the wide breadth of them. But yeah, same thing as last time. We'll do predicted products, and we'll do 1 or 2 variants. Just to kind of increase the substrate scope, right? Or see what it is that we can do with the molecules that we have. Cool. So starting the first one, we have an acyl chloride. We have this amino alcohol. So remember, acyl chlorides, acylating agents, they'll throw their acyl group at any nucleophile in solution. So we have two competing nucleophiles, oxygen and nitrogen. I think usually, right? I mean, really, it's normal to feel that the nitrogen should be the most nucleophilic atom here, just because it's less electronegative, more basic. But if we were to acylate, you might notice that we would form this interesting acylated compound where this nitrogen has a cation that we can't really resolve. And you might also remember something that I said in the last video about, hey, if you have a nitrogen with no protons, these guys are very good bases, right? They're non-nucleophilic. And for that reason, really. So in fact, this was a bit of a trick question, so I apologize. But this is actually going to form the ester. Okay, so this will form the ester here. So look out for that, right? That's that trick question. Just be careful of that. Okay, cool. In terms of variants, there's not very many variants here, actually. I guess you could have done like a Jones. So maybe we could have done Jones first. That does this. Jones would just protonate this amine. So it defunctionalizes the amine, essentially. Nothing too crazy is going to happen there. And then maybe we do like a Fischer esterification or something like that, or some kind of SLCO2, some kind of reaction that changes the acyl chloride into, or sorry, the carboxylic acid to like an acyl halide or something, right? SLCO2 would work here, right? So possibility, open to it, but there's not much else you could do with that. Okay, cool. All right, move on to the next one. This is a great example of chemoselectivity, right? We have an ester, and we have an acyl halide. And so a lot of these guys share nucleophiles. Like, for example, if I react with lithium aluminum hydride, that just, that's a very universal experience of forming the primary alcohol on the ester and the acyl halide. So both would react here for sure. But what we're using here is a Gilman, which I hope you guys remember, Gilman only reacts with one of these, right? Gilman's a very mild reagent. And so it only reacts with the most reactive carbonyl groups, right? Those really just being the acyl halide, right? And technically the anhydride too. So this Gilman will add to the acyl halide, but it won't touch the ester at all, right? The ester is completely inert. It's completely resilient to that. And so, I mean, a great rule of thumb is if something won't react with a ketone or an aldehyde, it's definitely never reacting with the ester because the ester is less reactive, right? The aldehyde is more reactive than a ketone, which is more reactive than an ester. So anything that won't react with these guys will definitely never react with the ester, right? It's not built for that. Okay. So what are some other chemoselective things that we could do, right? Well, another one we could do is NABH4. That would essentially accomplish the primary alcohol reduction of the acyl chloride, leaving the ester alone, right? NABH4 can't reduce esters, right? Is there anything that we could use that would only reduce the ester instead of the acyl chloride? And that there is something. There's Dibble. If I use one equivalent of Dibble, remember Dibble's an acid. So the more basic carbonyl is the one that's going to react here. That's going to be this guy here. So Dibble would be able to accomplish that deprotonation, or sorry, that reduction there. Is there a way to only react with the acyl chloride in the same manner, right? And there is, right? We can use LIPA or the lithium aluminum trialkoxy hydride, right? That would only react with the acyl halide. Okay, so look at that chemoselectivity, right? So much stuff we can do. Here's the cool thought, something to think about, right? Let's say that I use some base here, right? LDA even, right? LDA or, like OR minus, right? Maybe particularly even this O minus here. Where do you guys think the first deprotonation would take place? Right, that first deprotonation. I mean, if I have to think of hydrogens, I have these here. These are all contenders, right? I would never even consider these alkanes, but out of all of these, right, we know this one for sure not, because this anion is just next to an oxygen, so it's only inductively stabilized. But we have, possibility of forming an enolate either here or here, right? Which enolate might be more stable, right? Use that 118A, 118A inductive thinking, I guess, or just think about what makes anions really stable. Definitely going to be the one in the middle, right? So this is something you'll talk about again, chapter 24, but you guys totally have the ability to think about this now, right? So if I were to do this and then like an RX, you can get an enolate alkylation that is, it seems like it's a bit out of scope, but it really isn't, right? We have learned to do stuff like this. Okay, so cool little reaction there. Okay, cool. All right, let's move on. We have an acyl chloride, and we have this, again, amino ether, or I guess ether amine. This should not come to a surprise to anyone, right? This ether amine actually has a name. It's called morpholin, but this will just make the morpholin amide. Okay. And for those of you that might remember, it's okay if you don't, but morpholin, what makes it kind of interesting is that it has this heteroatom with the lone pair in its chain. So if I were to actually do a Grignard here, right, this Grignard would actually stop at the ketone because in the reaction, when we add the R group, right, the magnesium chelates, or it sticks to, right, this oxygen, and it makes it a bit more stable. That one addition, right? We don't get that elimination of the nitrogen group and have the second addition occur. Okay, cool. So that's a reaction that we could do there. What are some ways we can riff on this? I mean, really, there's just doing like Dibble, or right, Dibble will give us the aldehyde. Litba would give us the not Dibble, Litba. Sorry, Litba would give us the aldehyde here. Right, so Litba would give us the aldehyde. What? Okay, sorry, I am like losing it right now. LiAlROR 3H would give us the aldehyde, right? R2CuLi would give us the ketone here, right? Whatever that may be. I guess maybe let's make it a bit specific, just to help you guys see more things. Maybe you could make it something like this. And so what is that? 1, 2, 3 carbon. So 1, 2, 3, right? Like that. So we'd have a ketone like that with the R group, right? Aldehyde possible. I don't really write this reaction very often, so I'll write it now. Imagine we reacted with the carboxylate, right? That would just give us an anhydride here, right? So possibilities, right? All the possibilities. Cool. All right. Moving on to the next one. So we have a carboxylic acid and we have a Grignard. And I know that this reaction was a bit, people were having a hard time with this. The number one thing to remember when it comes to reductions of carboxylic acids, and even those of like amides with protons, is that these protons here are acidic, right? On the carboxylic acid, this clocks in about 5. On the amide, this clocks in about 15. Okay. And because they're acidic, bases will be able to pull these guys off, right? So if I have a base, right, really the first thing that should happen is this deprotonation, right? So just something like that. Okay. And so this was that explanation question on the last midterm, which was, hey, if I have a carboxylate and an ethoxide, why don't I get a substitution? It's because carboxylates are stable, right? Same with amidates. Amidates are somewhat stable. And so weak nucleophiles like these guys are not relatively weak, I should say, right? These are not the strongest possible nucleophiles, right? But nucleophiles like ethoxide are not going to be able to break through that, right? But if you do have stronger nucleophiles like Grignards and hydrides and organolithiums, right? Those guys can blast through anything. And so that's why with lithium aluminum hydride, yes, we do go through the carboxylate first, right? So that first deprotonation is lost, right? Or that first hydride is lost in the deprotonation, but we still have, 3 more hydrides, right? So we used 1, and we still have 3 more, right? So we could potentially get another reduction and then another reduction on top of that, because there's 4 of them, right? So what happens when I use one equivalent of a Grignard? Or I use, a Litba, where I only have one hydride, right? If you only have one, then all you can do is a deprotonation, right? So if I have, let's say, the lithium aluminum OR3H, right, where I only have one hydride, or I have one equivalent of the Grignard, right? I mean, I can only really get one thing here, which is the deprotonation. So this is probably the question you're going to be asked, right? When it comes to carboxylic acid, one equivalent reactions, stuff like that. It's just so you remember, oh yeah, that's a base, right? That's going to deprotonate there. Now, if this were at 2 equivalents, or really at 3, 3 is like the magic number here. What you would get is a ketone. So you can make ketones from carboxylic acids. It's not the best reaction in the world. But it is, I mean, it is possible to do. I believe it's in, on industry scale, right? They tend to just do this reaction. But right, you can just ignore that too and just go with the one equivalent here. That's just new to deprotonation. Okay, cool. So just keep that in mind, right? We could have had this also as like an amide, right? And we have CH3Li, strong base. Remember, that's always going to just deprotonate on that position there. Okay, so that's what you're going to get. Cool. All right. So I'll probably write in this one as the variant. There's not much, I mean, what else can you do, right? You can just heat this up, make a symmetric anhydride, and other carboxylic acid reactions. Cool. All right. Looking at E, first step does the MgBr, and then adding in CO2 gives us the carboxylate. We could protonate this. It doesn't really matter because step 2, we need to use SOCl2, which is functionally going to replace this with Cl. And Cl with LitBa is just going to give us an aldehyde. So we're going to get that there. Okay. If I use the Gilman, so if I use, let's say, CH3 to CuLi, right, I would just get the ketone. If I used a nucleophile like morpholin, I would just get the amide, right? Stuff like that. So pretty straightforward, I think. This actually also is that substrate that we talked about, right? This could be a great explanation question, right? Why can you not use the CN pathway for this? So why is it that we use the magnesium pathway? Why can't we use the CN pathways? Because you can't do SN2 on the center, right? So that could be a very good explanation question. No SN2 on sp2, right? It's almost rhymes, right? So it's a little jingle you can have playing in your head. Cool. All right. Going on to F, right? NABH4, remember that reduces, very electrophilic carbonyls like acyl halides, ketones, and aldehydes. It does not touch esters and carboxylic acids though. So first step, right, we're going to have an intact carboxylic acid. It might even be the carboxylate, but who cares? Because step 2 is actually that should be, that should not be water there. I'll have to make a correction on that. Oops. But hopefully those of you that are doing this can see what I was trying to do here. It's just meant to do that. So we make a 5-membered ring here, form the ester, right? And then there's like a methyl here, I think. Yeah. So cool. All right. Oh, and the methyl here. So that's our cyclization right there. Other things we could have done here. I guess you also could have, instead of seeing this, you could have seen SOCl2 and pyridine. Okay. I already know there's going to be people that, there's going to be the well, actually kids that say, well, actually, I remember from 118A that alcohols can react with SOCl2. And alcohols are better nucleophiles than carboxylic acid. So won't that actually mess up your reaction, because that will turn this into Cl and then nothing will happen? Ha ha ha. And I mean, that's great that you remember that. I'm happy that you guys are remembering things. That's always a plus. But keep in mind that we're doing this in pyridine. So actually what the first thing is going to happen is the carboxylate is going to get deprotonated, and carboxylates, the conjugate base, are stronger nucleophiles than hydroxyls, right? The hydroxyl will not be deprotonated by pyridine. So actually, yes, SOCl2 will work as intended here, where it will make the acyl chloride, so long as you don't do this reaction in excess. So this would be a reaction where I would have to meticulously weigh out exactly how much SOCl2 I put in, right? Because you don't want to accidentally overdo it and get this one to react too. That is possible. But I guess that won't be too much of an issue, because once you make the acyl chloride, you can imagine this instantly cyclizes. So this is also a viable pathway to this. Okay, cool. I can't really see any other thing you'd want to do here. Maybe just one step of lithium aluminum hydride, just kind of demolish the whole system, right? Just form that, could do that, right? That's about it though. Cool. All right. Moving on, we have HCl, heat, and carboxylic acid. So a lot of people were a little stuck on this one, a little confused, because we did talk about how HCl is not a good way of making acid chlorides, right? Because once you get to here, I'm skipping a lot of steps here, right? Because I just want to get to this point, right? No matter what you do to that alcohol, make it water, right? Cl is always what's kicked off. So in every single case, HCl will never make the acyl chloride, but that actually works in our favor, because all that means then is that the only capabilities of HCl is that it can protonate the carbonyl. And then just think about it, if I have a high excess of this, which I usually will, right? I have a lot of this carboxylic acid. All there's left is more carboxylic acid, right? And so this is a nucleophile that can go ahead and attack, right? Remember, we normally just see carboxylic acids heated together and they cyclize. So if you add acid catalyst, it's going to make this reaction even faster. And what you get is the symmetric anhydride. Okay. Now, a lot of people are wondering why this reaction works, because you're making an anhydride, which is super reactive. Well, the term anhydride, right, that actually comes from the fact that if you put a carboxylic acid in dehydrating conditions, so in conditions that will pull water out, right, you will make them anhydrous, you will form the anhydride. So they dimerize as a result of this, right? It's pulling out water. So usually what you'll see in this is some kind of dehydrating agent. Common ones are like PLCl3, no, not SOCl2. SOCl2 is a little tricky. That won't really do it. But POCl3 will do it. P2O5 will do it. Things that you guys don't really know about. But these are things that pull out water, right? They suck water out, and that, as a result, forms these anhydrides. Okay. You usually also need to blast this thing high temperature, right? Unless it's cyclic, right? That's why usually these reactions are restricted to the cyclic versions, because you can just heat this. You don't have to really put in a dehydrating agent, although it'll make it faster, right? Like SOCl2 is a dehydrating agent, POCl3, right? P2O5. Those guys will pull that water out. And this will be, you have to do this at a way lower temp than you normally would. Okay, cool. So let's keep that in mind, that's possible, right? Usually reserved to cyclics though, right? Because cyclics are better. Cool. All right. Not very many ways to change this other than, changing like doing carboxylic acid reactions. So it's kind of boring. All right, moving on to H, we have LiAlH4. Remember that LiAlH4 is the mother of all reducing agents. So get this, like MOA, right? It's the mother of all hydrides. Absolutely. I guess, no, it's still MOAP. It's the mother of all bases, I guess. It is technically a base. But anyways, super strong reducing agent. You can imagine will not only reduce the aldehyde, but also reduce the ketone into the alcohol. So what are some riffs on this? I could do NABH4, right? Which again, if NABH4 won't react with esters, it definitely will never react with the mids. So we will get only the carbonyl, the ketone reduction there. If I do dibble, right? Dibble is an example, one equivalent of dibble, right? That will give me the selective reduction at the amide. Sorry, not that. It will give me the selective reduction where we cut here to get this, right? The aldehyde, the keto, I guess the oxoamino aldehyde given there. Let's say that I did, Grenier would be kind of tricky here. So I guess you can kind of guess. If I did an excess of like CH3Li, right, that would absolutely eviscerate the system. Get the symmetric alcohol out here, right? Cool stuff, right? Cool stuff. I guess one thing I also don't do very often is hydrolysis reactions, just because those are just, hydrolysis doesn't really do much, right? It just kind of turns something into the parent, which is the carboxylic acid. Just keep in mind, right? If I have if I'm in acid, I make the carboxylic acid. If I'm in base, I make the carboxylate. So I know that's really ugly. It'll look better on the key when I draw that out. Cool. All right. We have here an ester, and we have excess Grignard. So, or organolithium, because I know some of you will be nitpicky with me saying Grignard there. So we'll get that. Right. We'll get this. Okay, cool. I guess if I did dibble, then I would just make the aldehyde, right? Let's say that I reacted with an amine, NH3, right? That would give me this here, right? Cool. All right. Moving on. J, we have this dioic acid or phthalic anhydride. And if we heat up phthalic dioic acid, if we heat it up, we get phthalic anhydride. So this is what we get if we heat it up. And if I react with ammonia and no heat, right, what I'll get is, right, the amide on one side of the anhydride and then the carboxylic acid on the other. Probably the carboxylic salt, really. That's what I should be saying, right? If there is heat, though, then we can get, right, we can get that closing into the phthalimide, which you guys are becoming more familiar with currently, I believe, in Gabriel synthesis in chapter 21. Okay. But yeah, this is usually what you'll see. I mean, you can kind of skip all this if you just do NH3 and heat altogether, right? It's like the same process. So it'll give you the same thing. Cool thing about this one actually is if you use a hydrazine, what you'll get is this structure here. It's a 6-membered ring. Okay, with this sort of like hydrazine bridge. I forgot the name of this. This turns into something biologically relevant. Forgot the name, but that's something cool you can do. You just got to heat it up. Okay. What's something else I can do? I guess lithium aluminum hydride would give me the diol, right? Yeah, that's about it. Cool. All right, predictive products. Hopefully that was helpful, and hopefully you guys saw a lot in there. Again, that whole idea of if I only have 10 problems, how can I extend it to 20, 30, 40, even 50? All right. So going on to base mechanism, or mechanism in general, hopefully, I mean, if you guys need help with mechanisms, again, please watch that, watch that mechanism part, the review part of the video. I think I went over that pretty well. Remember, bases are super simple. You kind of just add. And then you just eliminate. Oops, sorry. There you go. Okay. Just remember, you always, in basic solution, right, hydrolyses will always do this deprotonation, because remember, when you're kicking off these groups, you're kicking off a very bad leaving group. You're kicking off an O-, or in the case of where this is a mid, you're kicking off N-. So why is it that we can even do this in the first place, right? Well, you have to understand that this is all equilibrium, right? These are all under equilibrium. So yes, this step here might be the slowest possible step. That's totally fine, right? It might be the slowest possible step, but all that requires is for it to happen once, so that you get this deprotonation that forces it to go this way. So this is almost exclusively towards the product. And then Le Chatelier's takes over, right? Le Chatelier starts saying, uh-oh, we're starting to lose, we're starting to form this product here. And we need, we don't have a high enough concentration of it. We need to stress the system in order to make more of this. And so more and more of this ester or amide, or I guess technically lactone, lactam, these are lactones. If this were a nitrogen, this would be a lactam, right? These lactones, lactams, we need to hydrolyze more of them, right? To reduce the stress and form more of this product, okay? So that's why this works, right? This whole Le Chatelier thing, okay? Cool. You can also try doing this the other way too, I guess, if you wanted to go from here to here as another mechanism problem. So you can imagine base would deprotonate here, right? And oh, actually, sorry, we don't, not from this. That'd be from like an ester. There we go. It's like a transesterification, right? Keep in mind that this won't work, right? Because this will just deprotonate this. So I guess, like, again, very good explanation problem, right? This will just stop here. It won't go any further. Okay, cool. But you could try this as an ester where you pull that off. This adds in. Right. And again, once you add in, you just kick off all that stuff. Cool. I guess another thing you could try is if you want to do this in acid. Remember, acid is a little bit longer, but you can follow that little thing, peptide, right? Protonation, addition, proton transfer, elimination, deprotonation. Cool. All right. All right. So this was the mechanism on the practice exam, which it's okay that this was. It's no big deal. It just means that we probably won't see it on the exam. So we'll just go through this really quickly. But pyridine can deprotonate at this position here. Right. And then we can add on the SOCl2. So I've actually looked into this, and you can get rid of the Cl immediately. I used to think that you had to do the, the kicking up and going down, but actually SOCl2 has a lone pair here. So this is technically quote unquote like a sp3 center. So it's okay if you do this kind of arrow here. And I've consulted with some friends, and they also agree that this is fine. Okay. But from here, right, it's not totally obvious, but you could add in the Cl. Right. Normally there's like a driving force, right? There's like that cationic oxygen that can do it. But in this case, there won't be. But now we just go down. And the reason why we kick off the oxygen, right, is because we form that SO2 gas. Oh, thank you. We form that SO2 gas. Right. And then this Cl will just salt up with the pyridine that deprotonated earlier. Okay, cool. So again, driving force here is this gas formation. That's why, it's totally possible that the Cl gets kicked off. This could totally be in equilibrium because Cl is still a pretty good leaving group. But what matters is that the second we kick off that O group, that OSOCl group, SO2 is formed, it's lost. It's never going to be able to reverse. Right? This is not reversible. Okay, cool. You could also, if you forgot about the pyridine, also do this without it. It's not required, right? You could totally do it without it. It just takes, this step here might take a little bit longer, right? But the carbonyl oxygen always is what's going to attack electrophiles. Let's go ahead and do it the faster way. And then once you're here, right, now it makes sense why Cl adds in, because it's cationic. Okay, but once we are here, right, we can do a Cl attacks H electrons go between C and O, and then again, we release out that SOCl2 gas. And what we get is the following, right? It's just that pyridine will have to, I guess we'll have to show, you can show it later, or you can show it now, that pyridine would neutralize that HCl. Cool. All right. I wouldn't worry too much about this one. It was on the practice exam, so it's not very likely you'll see it on the actual. All right. And with that, we'll talk about synthesis. So I did, look at the synthesis on the practice, and it looks like it's, it looks like you also need some 118B reactions. That isn't totally out of the way. So we'll do the ones we have now, and then I have two more in mind that we can consider and talk about that have more 118B-esque, remnants of 118B. But hopefully you guys tried these. I'm going to assume you did. Okay. As always, the first thing you always get rid of in any of these is, get rid of a derivative, kind of destroy it. Because if you, derivatives are, they're always made from another derivative and a nucleophile, right? So I can imagine that there are two things you might think could form here, right? You could either have the carboxylic acid or the acyl chloride reacting with ethanol. So either ethanol and pyridine or ethanol with acid and heat, right? Depending on what you choose. Of these two, right, which one I would go with, the safer option is the carboxylic acid. And the reason for this is because whenever you have an alcohol and an acyl chloride in the same molecule, remember that they can sort of react with each other. I know a lot of you thinking that, oh, that's totally not possible that this would form a three-membered ring like that. And I agree with you guys. It probably wouldn't. It probably would not make this like really bad triangle ester. But you have to think outside the box here, right? It's totally possible that two of these react with themselves. So it's totally actually possible that we get a dimerization. This is actually a lactic acid derivative, kind of. But anyways, it's totally possible they could react with themselves. So generally speaking, if you're going to go with a route, go with the acyl chloride, unless there's some nucleophile down the chain, then it's actually safer to go with a different option like the carboxylic acid, something that's less, reactive. So I'd actually go with this for that reason. Okay. But again, as long as you recognize that you can get rid of that derivative, that's the important part, right? That means that you have chemical intuition, even if you don't have the correct sequence. Okay, cool. And now from here, right, hopefully you guys can notice what this is. This is an alpha hydroxy acid. And there's sort of two ways to make these guys, right? You guys might remember there is the HVZ pathway, which says, okay, I have a bromide where that OH is, and then there was a hydrogen where that bromide is. Okay, so there's a hydrogen here. That's one thing that's what HVZ says. And so we can kind of compare the starting material to the acid that we'd have to make. If I kind of look at my carbons here, I have 4 here. Those 4 are these here, right? This carbon is a little bit of a hard one to deal with, because we have to somehow transform this nitrile into a carbon that we can then transform or add on to another carbon, right? So we're trying to figure out a way. I mean, if we think about things that we can do with nitriles, well, one thing you can do is you can turn them into CH2, NH2s, I guess, but that's not really going to help us, because how do we turn NH2 into acid? We don't know how to do that. It's almost impossible. Maybe we turn it into an aldehyde, right? Or a ketone. But if I take this carbonyl, right, if I add anything to it, like a nucleophile, I'm guaranteed at least a hydroxyl. Okay, so at least the HVZ pathway is not the best possible pathway. It definitely is a headache of a pathway, if anything. So we don't have to go that way. But the other way we could go through is the aldehyde, actually, right? Or we can go through the cyanohydrin. So the aldehyde pathway actually is the way we want to go. The cyanohydrin is what signals that to us. Okay. H plus H2O and heat. Okay. And what we get out, so this will be Dibble, is going to be our answer. Okay. So again, always there can be multiple pathways. We just have to figure out which one's most optimal. And if either one is optimal, then we just choose one of them. Right. I think really for me, what the giveaway is that this is an aldehyde also, or sorry, cyanohydrin, is the fact that we added a carbon, right? We went from these 4 carbons here to this extra carbon here, right? So that just signals to me that we need to do like a CN type synthesis. Right. That's like the most obvious thing to me there. And so CN, especially with this alcohol, that alpha hydroxy, it's a really good signaling element, right, for this type of reaction. Cool. How are some ways we can change this? We could have done like RMGBr here, which just puts an R group here instead. And so that just has an R group that kind of tracks throughout the reaction, right? Just one to kind of throw everyone off. So that could have been there, right? Could have done something with that. Cool. So what are some other things that we can do, that incorporate more 118B style reactions? Well, one reaction for 118B that's particularly important for making carbonyls generally is the HVZ reaction. Or sorry, not HVZ, ozonolysis is what I meant to say. So if I wanted to make, or let's even start from a different substrate here. I guess I could have started from an alkene here. I could do ozonolysis, which gives me the, I guess I'll draw it like this so it's easier for you guys to track out what's going on. Right, I could do this aldehyde reaction here, and I could do Jones. Right. Obviously, I can't make the alpha hydroxy that I wanted to, but maybe I don't know, do HVZ or something. Right. Cool. So what are some things that I could do to figure out from this product here all the way to this here? Right. Well, first things first, right? I have an alpha bromide. That is, I mean, without a doubt, that is going to be HVZ, right? And so from here, now I just got to figure out, okay, how do I make a carboxylic acid while also losing a carbon, right? So how can I do a CC bond destroying step? And really, there's only one way to do this. You would do ozonolysis, right? Ozonolysis would give you that loss of a carbon. And remember, you just cut across the bond there, and you just kind of add a O to either side of that cut, and you get this. A lot of you guys might also be thinking, oh, can't you just use hot KMNO4? And yeah, you can totally do that. I mean, just personally, why I don't use this is because I mean, for me, this is not very practical. Hot cam NO4 is like the most oxidizing. It's the most like, if you wanted to destroy your substrate, this is what you would do: is you would throw it in hot cam NO4. Oh, sorry, this should not be an aldehyde. This should be an carboxylic acid. Apologize. So I mean, either way, either one of these would work. They would both be accepted, to be honest. But I know a lot of you would probably just rather do it this way because then it's just 2 steps, right? So it's a likelihood, something you could do. Not something that is not, it's not unallowed, right? I guess it's not that it's not allowed, but cool. So that's something that's more 118 B-esque, right? Another 118 B-esque reaction is, Jones not the only thing that facilitates this oxidation. You could also use MCPBA, right? MCPBA also works. And so remember that whole thing with ketones as well, right? If I use MCPBA, ketones form esters, and particularly esters on the more substitute position. Okay, we'll actually see something really cool you can do with this in my upcoming one. So we'll do the next one that's this, and then we'll do another one. And I kind of already spoiled a special step now. It will involve that MCPBA. Cool. All right. Moving on to this one. This one should have been fairly easy, actually. I think most of you guys can see what's going on here. If I kind of trace out my original carbons, because there's no real derivative here for me to look at, so I have to do some other kind of analysis. You guys can kind of see that we've kind of lost this acyl group for this amine here. And like I've always mentioned, right, you can think of this as losing a carbon. I like to think of it as you're losing that acyl group, right? You're losing that entire acyl group. This is a very clear indicator of the Hoffman. And so we know how to do Hoffman. Hoffman requires us to go through the primary amide. Very, very important. We have to make a primary amide. So we got to do NH3 delta here, and then we'll do our Br2. I got this question a lot this week. Does it matter what the halogen is? No, it does not. No, it does not. So it could have also been X2. It's just a matter of what's easier to use. Okay. But we can get our Hoffman here. Okay, it gives us our amine. Now, a lot of you are probably going to think, oh, why couldn't I have just done the amidate alkylation to add on, right, this group here, and then did my Hoffman? That's a great thing to propose, right? It's a great thing to think. And this could be a great explanation problem as well, right? Hoffman requires that this is primary because you need 2 protons. You need 2 protons for Hoffman. Okay, you need those. They're absolutely required. So that could be a great place for a mechanism, or sorry, explanation question. Definitely expect something like that, right? Right. Cool. All right, but still now we got to figure this out, right? How do I get that group here? How do I get this group on, right? Some of you were also kind of thinking about doing this sort of alkylation reaction where you use this as an SN2 nucleophile and it adds in. And again, this is not a bad idea, but hopefully with this upcoming chapter, you realize why this is not the most optimal pathway for this. So we got to figure out a different way to make this CN bond. And maybe it might be useful to think, how else can I make CN bonds or bond a nitrogen to a carbon in this chapter, right? Was there a group that will give its, functional group that contains carbon to any nucleophile in solution, right? What we're thinking of here is an acylation, okay? Acylations form this NC bond, right? That we can then reduce into the given amide, or sorry, the given amine, right? This is just LiAlH4. Okay. So consider this a way, especially in chapter 21, to make CN bonds. CN bonds are valuable, especially in modern organic chemistry, but they're also very hard to make because the SN2 is not as simple as you think, right? As you'll talk about, there's a lot of over-alkylation issues. And so you can't just take an amine and an alkyl halide and just add them together. So the answer is take an acyl halide and just reduce it. That's one of the answers. That's one of the possible answers you can make, right? Another good giveaway is that we're adding we're forming a bond with a CH2, right? We're forming a bond with a CH2 here. Okay. If you're forming this NCH2 bond with some alkyl chain, very, very common very, very common fragment for, hey, do an acylation into a reduction. Okay. Which actually reminds me, we'll talk about this actually after we think of variance, or actually, let's just, we can talk about it now, because this is the end of this one. But this guy here actually has a lot of fates like this. So we could, how we go to the aldehyde here, and we go to the cyanohydrin. I realize this is something worth mentioning, right? You can actually do a reduction here into making this compound here. So you can make this like really weird amino alcohol, or amino alcohol that you can then like acylate, right? You could just add like a, maybe we'll use an anhydride this time because we don't really use this very often. And I don't want you guys to think that they're like defunct or anything, but look at that, right? We can turn this into an amino or an amido alcohol simply by reducing the nitrile into the CH2NH2. Okay. So what's really important here is that the nitrile fragment is CH2NH2. If that's what you're adding, that's a nitrile, right? The fragment that we were talking about is an N-CH2 bond. So really, how many protons or how many R groups N has is ambiguous. What's really important is that what we're adding is a sort of like CH2 group to the N, right? If you're adding like a CH2 group to the N, that's a very good indicator of the lithium aluminum hydride reduction. Okay. You can actually, I guess you could do a amide. You could do an amide alkylation here, or amidate alkylation. Sorry. Right, that's possible. So you can get, you can afford some, you can do like a dibble. So you can do diabal, dibble, whatever you want to call it. NaCN. Sorry, my handwriting's getting bad. Hydrolysis, blah blah blah. It's steppy, but just things to think about, right? The hope is that I'll draw something that sticks in your brain and maybe it shows up on the exam. Cool. All right. So ways to riff on this one. How can we change this one up? Not much to riff, right? The biggest point was the Hoffman. That was the biggest point. I guess actually a riff that you could do is that, when we get to here, NH3, actually, let's even just do this. Let's say that I added in the benzylamine and I heated this up. So I get the benzylamide. Right. Imagine if I did lithium aluminum hydride here. Right. This would also give me that CN bond. Right. But look at this. Look at how this differs from this here. Right. Technically, these are almost the same. Right. These are both secondary amines with these two alkyl chains. What's important to notice here is that the carbon chain is retained. So don't think that Hoffman's the only way to get that amine, right? We can also do this through lithium aluminum hydride. Just a matter of how many carbons are in that chain, right? So this is a possibility. I guess you could do like an acylation or something at the end here if you wanted to. Right, just increase the number of steps, I suppose. Look at this, making this tertiary amide. Looks so wonky and crazy, but it's totally plausible. It's totally plausible how to make this. Okay, cool. All right. So like I was saying, the reactions, you are required to know a lot more reactions because now you need to know alkene reactions as well. So this is what I thought up of while I was, while I was thinking today. Originally, this was only going to be a student special, so people that I was, I was only going to show this to my students, but I'll show this to you guys too. But you guys might remember this one from yesterday. Okay. This molecule here, do something cool to it. Okay, cool. So we're turning this from this acid chloride, so ester acid chloride, into hydroxybenzoic acid. Okay. Now, when you look at this, a little bell should ring. And if it doesn't ring, it's okay, I'll ring it for you. Okay. If I kind of think about carbon count, again, for the most part, carbons are there, but we're missing a carbon. We've lost a carbon. Now, again, usually when we think of loss of carbon, the number one reaction that sparks to mind is the Hofmann, right? Where we go from here to here, right? We think of this reaction here. Or sorry, I guess this is what I was going to try to say, is this reaction here. So we have this reaction where we can replace the acyl, lose a carbon, and have form an amine. But there really isn't, at least we haven't discussed explicitly we haven't discussed explicitly. Sorry, I don't know why am I stuttering? We haven't really gone over explicitly a way to do this with an oxygen, or is there a way to do this where I get like a Hofmann type transformation, but I form an alcohol instead? Well, lo and behold, we do have a way of doing this. And I'll tell you what, if you want to, pause and try this. The hint that I gave you was what I said earlier in that first synthesis. I showed a reaction that you're going to want to use, and that will help you get to this. Okay. So that reaction was the MCPBA reaction, which was to say that if I have a ketone, right, I can insert an oxygen in to form an ester. So my hint is that an ester is involved. So if I try to think about how an ester would be involved in this, well, actually, I already know how one ester is involved, right? One of these esters was right here. And so essentially, if I'm going from ester to acid, I'm doing a hydrolysis. So if I'm doing a hydrolysis and I need to use an ester to form this guy, you can imagine then the ester was this guy here, which means that if I did an MCPBA reaction, this ester was already there, so I don't have to worry about it. This ester was formed by this ketone here, which means that earlier, that regioselective reaction we talked about, CH32 CuLi, is actually the key to this reaction. So what's going on here, right? We are turning selectively the acyl chloride into a ketone, which we are then oxidizing into the ester via MCPBA. And remember, the more sub side is the side that migrates typically. So the secondary side is what's, or I guess, you can see how that's more sub, right? It's not technically secondary, but whatever. Anyways, we are adding the oxygen in, and then we're hydrolyzing it out. So it's like, in a way, doing a Hofmann, right? Just kind of in the opposite direction, right? Hofmann would require that we form the NCO, which forms, this carbamic acid, and the carbamic acid decomposes. Well, in this case, right, all we need is the ester. We can just hydrolyze that, and out we get as the species here. Okay, so cool little reaction, hopefully. And it's a way of doing that Hofmann-esque transformation just on, just with an alcohol. Okay, so thinking outside the box. There was actually, I remember seeing this. They actually do this in steroids. So there is a steroid known as pregnenolone, I believe. I should know the name of this, so it's a little sad that I don't. But anyways, steroids look like this. Pregnenolone. If you want to oxygenate, or if you want to turn that into an oxygen, you turn this into an acetate, and then you hydrolyze. Okay. I think I remember seeing that when I was looking into research into steroids that I could work with, and I used to work at Davis. Cool. All right, so that's it on the synthesis front. I just wanted to get out some old reactions. Remember, anything that you can make a carbonyl with, it's a good one to know. Just a reminder, you can do the R2BH reaction with alkynes to make aldehyde. So for whatever reason you start from an alkyne, you can do that. That can turn into an acid and then do acid reactions. Again, if you have like a ring with an alkene in it, you can excise that ring, form a ketone on the methyl end, form an aldehyde on that end. A lot of you guys are going to be very tempted to do the KMNO4 reaction, which you can also do. They'll just give you an acid, right? Stuff like that. Cool. All right. And then I'm not sure if you guys need to know this, but I will remind you of this, right? If you have a methyl ketone, you can do the iodoform. I don't remember how emphasized this was, but this makes a carboxylate. So cool. All right. That being said, we'll call it on synthesis there. I think we're making pretty good time. I think we might have hit 45 minutes though, so I'm gonna have to speed this up. Cool. Explain why this won't work. It should be pretty simple, right? We have an amide, we have an acetate. So if I think about the tetrahedral intermediate here, right? Never really is there a case where this minus comes down and N leaves first, right? Acetate always leaves. So the general rule of thumb is that you want your nucleophile to be a stronger base, right? So the issue here is that this is a weak base, right? And this here is a strong base. You want this to be reversed. You want your X group to be a weak base, and you want your nucleophile to be a strong base, relatively speaking, right? Because that will promote the addition of the strong base and the elimination of the weak base, so elimination of the X group. Okay. So what's usually the solution to these kind of problems is you just use a strong, a weaker base leaving group. So acid chloride is the typical solution to this. Okay. But again, you can imagine many different variants of this question. In the sense that, you could start from here and say, oh, why doesn't this work, right? Because O minus versus S minus, this is a strong base, and we want that to be a weak base, right? Oh, here's a good one. I can't remember if I talked about this in the last one. Why can't we make phenyl esters from esters, right? Why is this such a hard reaction to do? Again, alkoxide is always a stronger base compared to a phenoxide. There's resonance involved, so it's a weaker base. So that's never going to happen. That's why we have to use acid chlorides to do those acylation reactions, stuff like that. So I think I covered a majority of these types of explanation questions. Other types of explanation questions you can see in case you can't watch the third video, which is totally fine, right? Why won't this Hoffman work? We kind of already talked about this earlier today, right? This Hoffman will not work because you need 2 protons to facilitate the Hoffman, right? You need an NH2, a primary amide, to do this. So you solve this by using your primary amide. Another type of question. So this was way back when I mentioned, this or this, right? Why you have to use, so why can't you use CN minus here, and why can't you use the Mg synthesis here, right? So you can try to think about this if you want. If you don't know, just check out the first video. It's in the reaction section, or sorry, it's in the synthesis section when I go over the slides, so you can zoom through the middle of the video where you see slides again and make sure that it's a synthesis part. And that's, that's the answer there, is why we'd have to, why do these not work? So this doesn't work, this doesn't work. We have to switch them in order for it to work. I guess another explanation could be the amidate alkylation stuff, right? Why would this amidate alkylation not work? And so you can think about why that is. We have these protons here that might be an issue, right? Stuff like that. So remember, anything you can think of where there was an exception or we had to think more about why we were doing something, that's a great explanation question. Always a great explanation question. Okay, cool. All right. With that, let's just get into the vocab. I don't know if you're going to have vocab, so I'll just speed through it. Cyanohydrin and then alpha hydroxy acid. Some of you might have put carboxylic acid here. Remember, it's specifically alpha hydroxy acid, right? You're specifically furnishing this compound here. So you need to know that term, alpha hydroxy acid. Okay, cool. Nucleophilic nucleophiles attack acid derivatives via addition elimination mechanism, which goes through a tetrahedral intermediate. Okay, cool. Remember what I said? I literally just looked at the vocab terms you need to know. I just made sentences that were true with them, which is what you guys should be doing. All right, circle the molecule that reacts the fastest with OCH3 minus. How many of you just did this instantly, right? Raise your hand. Just be honest. I imagine a lot of you did that almost instantly, which is fine. That makes sense that there is a nucleophile and you thought the acyl chloride reacts the fastest. Just remember that this is a strong base nucleophile, right? Strong base is like protons first and foremost. So actually the fastest is going to be this guy here. Okay. It would be the same if I had an NH2, right? Because again, this clocks in around 15, so it's about the same. So these two always win in the acid base realm, right? Acid base is always faster than substitution. Okay. So if I had used a weaker base, so let's say I had used HOCH3, so methanol, then yes, this would be the answer. That would be the answer. But because I used a strong base version, we want to look for the most acidic proton first. Cool. All right. Circle the molecule at the highest boiling point. It's super practical, right? We talked about this. If this were not true, we would all be puddles of water. the amide has to be the highest boiling point. Okay, this has to do with the derivative trend, right? There's a lot of resonance, so there's extra forces you have to break through. Cool. Figured out. I'm not too inclined of doing this NMR problem because based on your practice exam, you guys are not going to get an NMR problem like this, which, you know, kind of sucks, kind of doesn't, whatever. But we can do this really quickly. We can learn some things from this, right? First and foremost, we have these broad peaks. We have an alcohol and a mid. So maybe one of these two guys. Remember that the cutoff is usually at 5 with sp2 being on the left, sp3 being on the right. Right, the alcohol is sp3, but the N being next to a pi bond makes it sp2. Right, so this is going to be F, and then this here is going to be C. All that's left now is 4, 3, 2, 1. You know, 4 is going to be the next most electronegative atom, right? That's going to be oxygen, so the proton next to that is going to be there, so C. Next is nitrogen, so G is right next to nitrogen, so that's going to be G. Next most electronegative thing is the carbonyl, so E is going to be the next thing, right? And then D is closer to, D is like kind of in between the oxygen and the carbonyl. A is only next to the oxygen. So 2 things deshielding D, 1 thing deshielding A. Look at that. In less than a minute, we finished this. Okay, cool. All right. So that leaves us with a spectroscopy question. Looking at this, I can already kind of have an idea what to do here. This one shouldn't take too long. I'll give you a hint. It's a biomolecule. So I wrote it to look like that. But if I do DOU, 5 times 2 is 10, plus 2 is 12, plus 1 is 13. 13 minus 11 is 2, divided by 1 is 2. Did I mess something up? It shouldn't be 2. Hold up. 5 times 2 is 10, plus 2. Oh, 12 minus, sorry. What did I get 13 from? 12 minus 11. So it's 1, it's a 1. It's a 1. Sorry, I don't know where I got 13 from. That's kind of funny. Anyway, there's 1 degree. So I'll look at this CNMR. What do I see? I see this peak here, right? That means a acyl derivative, right? If I think about it, the easiest thing to figure out is if it's a carboxylic acid, there should be a peak at 12 ppm. If there is an amide, right, it should be 1680 in the IR. If it's chloride, there should be a chloride in the formula, and there's, you know, it's like 1810 in the IR. Ester is kind of like if it's not any of these, it's the ester. And then hydride usually has a bunch of IR peaks because it has 2 carbonyls, and then there's usually about 2 lines here. I see the acid peak, right, the 12 ppm. So I know this is a carboxylic acid. So that's pretty easy. There's a nitrogen in the formula, and there's a 2H singlet here. So that tells me that I have an NH2 like this. I see a 1H multiplet, 6H doublet, which hopefully you guys remember, that's the isopropyl peak. And then I have this 1H that's around 4. So that tells me that there is a 1H with 2 things connected to it that I'm not sure what they are, but I know one thing here is going to be NH2. It has to be, because it's all the way at 4. So it's the most electronegative thing. Okay. So with that being said, then, I mean, I can get rid of this piece now because I know where that went. I have an amine with 2 things I can connect to. I have this isopropyl and I have this acid. Guys, come on. It's just like Legos, right? If I put this all together, what I get is this here, which, hey, hope you guys recognize this is alpha amino acid. This is valine. Okay. How do I remember valine? It has a V. So it's super, super easy to remember that one. Okay. So amino acids, what really gives them away is this peak here and this peak here. It's like they're iconic peaks. I guess, like, you know, if you see these, you know, it's an amino acid. Maybe the more interesting amino acids to use are the ones that are also derivatives. So there's technically 4 of them, but they're the same thing twice. You can have the glutamic acid or glutamine, or you can have aspartic acid, which I accidentally drew too many of these here. Aspartic acid is shorter than glutamic acid, or asparagine, right? Which I believe, I know the code for this is Q. Is this one asparagine? I think it's N. Pretty sure it's N, right? These guys are a bit more interesting because they're derivatives. So you can imagine, right? This would have like an acid, like a mid peak. This would have also a mid peak. So it'd also have a 1680 in this on top of the 1750, right? Stuff like that. Or if it's the acid version, so the aspartic and glutamic acids, right? They would just have another carboxylic acid peak. So there'd be another peak here. Cool. All right. Well, that's all I want to cover now on this. I'll get gym term 1C done, but again, don't worry about that one too much. That one's more of my fantasy for what should be the exam for this class. Cool. All right, I'll try to get this key out as soon as possible. If there are any questions or anything I messed up, because I probably did mess up something, just let me know. Okay, cool. Guess have a good one. See ya.